day everyone, I am here again, Rhea B. Hirana, a BSc Science. For today's video, I will be going to compare and contrast the three theory of light. So the first theory is the particle theory, second, wave theory, and third is the particle wave theory. So what is particle theory? In optics, the corpuscular theory of light, arguably set forward by Descartes in 1637, states that light is made up of small discrete particles called corpuscles, which travel in a straight line with a finite velocity and possess impetus. This was based on an alternate description of atomism of the time period.
Sir Isaac Newton's corpuscular theory was one of the earliest scientific attempts at understanding the nature of light. Even though it was originally set forward by Pierre Gassendi, it was Newton who had later developed and proposed the corpuscular theory of light way back in the 17th century. However, after 100 years of existence, it later gave way to a more popular Huygens wavefront theory that could explain some of the limitations of Newton's corpuscular theory. Newton's corpuscular theory of light states the following. Light consists of corpuscles, which are a stream of discrete, tiny, light, and perfectly elastic particles. Every luminous source, like the sun, a lamp, or a candle, emits these corpuscles. These corpuscles travel in straight lines in all possible directions. The rate at which these corpuscles travel may differ depending on the medium in which they disperse. The vision of human beings is a consequence of these corpuscles falling on the retina of the eyes. Various colors of light are due to the difference in sizes of these corpuscles. These corpuscles could perfectly explain the concepts of reflection and refraction of light. The reflection of light, which consisted of corpuscles, is just like the reflection of a perfectly elastic ball. Consider the case of a perfectly elastic ball that hits the wall, which is a rigid plane. When this ball hits the wall normally, it bounces back and travels along the same path that it takes during the throw. However, when this ball is thrown at an angle to the wall, it bounces back and away from the wall at an equal angle with respect to the normal. However, it takes the opposite direction. The angle of incidence, I, of the ball is equal to the angle of reflection, R. Reflection of corpuscles of light follows the same rules that reflection of this perfectly elastic ball exhibits. In other words, each of the corpuscles behaves just like an elastic ball. This means that when corpuscles hit the surface normally, they travel along the same way back, and when they hit the surface at an angle, they are repelled near the surface and reflected back such that the angle of incidence, I, is equal to the angle of reflection, R. According to Newton, the refraction of light was due to the supposed change in the speed at which they travel, thereby causing a resultant change in the direction whenever these corpuscles enter from, say, a denser medium to a rarer medium. Although Newton's corpuscular theory of light could successfully explain the reflection of light, his assumption of higher velocity of light in denser medium as compared to the rarer medium has been disproved. He was also unable to validate his supposition that various colors of light are due to the difference in sizes of these corpuscles. For these reasons, the hypothesis was rendered baseless. The biggest limitation of Newton's corpuscular theory of light was that it could not illuminate the phenomena of interference, diffraction, and polarization of light.
How about the wave theory?
Huygens wave theory. According to Huygens, light is propagated in the form of waves through a continuous medium. Huygens assumed the existence of an invisible elastic medium called ether, which pervades all space. The disturbance from the source is propagated in the form of wave through space, and the energy is distributed equally in all directions. Huygens assumed that these waves to be longitudinal. Initially, rectilinear propagation of light could not be explained. But the difficulty was overcome when Fresnel and Young suggested that light waves are transverse. The wave theory could satisfactorily explain all the basic properties which were earlier proved by corpuscular theory, and in addition, it explains the phenomena of interference, diffraction, and polarization. According to Huygens, the velocity of light in a denser medium is less than that in a rarer medium. This is in accordance with the experimental result of Foucault.
And lastly, the wave particle.
Do we see it? Is it a particle, like atoms? Or is it a wave, like ripples on the surface of a pond? Scientists in the modern era would spend a couple of hundred years figuring out the answer to this question. Isaac Newton was one of the earliest. Newton believed that light is made up of tiny, atom-like particles which he called corpuscles. Using this assumption, he was able to explain some properties of light. For example, refraction, which is how a beam of light appears to bend as it passes from air into water, But in science, even geniuses sometimes get things wrong. In the 19th century, long after Newton died, scientists did a series of experiments that clearly showed that light can't be made up of tiny atom-like particles. For one thing, two beams of light that cross paths don't interact with each other at all. If light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the two particles involved in the collision would bounce off in random directions. But that doesn't happen. The beams of light pass right through each other, as you can check for yourself with two laser pointers and some chalk dust. For another thing, light makes interference patterns. Interference patterns are the complicated undulations that happen when two wave patterns occupy the same space. They can be seen when two objects disturb the surface of a still pond, and also when two point-like sources of light are placed near each other. Only waves make interference patterns, particles don't. And, as a bonus, understanding that light acts like a wave leads naturally to an explanation of what colour is, and why that pencil looks yellow. So, it's settled then, light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets, called quanta. But we can't just forget about properties like interference either, so these quanta of light aren't at all like the tiny hard spheres Newton imagined. This results that light sometimes behaves like a particle, and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics. So, after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either.
That's all for this video.